All right, today we're looking at exponential growth, but with real-life applications. Okay, we're going to keep using the whole 0, 1, 1b thing and all that, but we're just going to apply it to some real-life things, and we're going to look at two formulas that come up a lot with exponential growth in real life. This very first one is y equals a times 1 plus r to the t. Okay, so when a real-life quantity increases by a fixed percent each year, this amount y can be modeled by taking an initial amount, 1 plus whatever that percentage is each year, and then raising this to the amount of years. So let's just define what all of these variables mean. A is our initial amount. Okay, t is the number of years. R, now this is the part where we have to be careful. R is the percent increase. Okay, it's the percent increase for growth. If it's decay, it'd be a percent decrease. Now, this whole 1 plus r, since the entire 1 plus r is being raised to our exponent, all of this is the growth factor. All right, so this is the base of the exponent. Okay, in 1996, there were 2,573 computer viruses and other computer security incidents. During the next 7 years, the number of incidents increased by 92% each year. All right, so let's just take that problem and let's try to figure out what variables we have. All right, so do I have my A, an initial amount?
2,573.
Yes, 2,573. Okay. During the next 7 years. So, like, the T is going to be, over 7 years. And then the rate. What was the percentage that it was increasing? 92%. How do I write that as a decimal? 0.92. Okay, the first problem says that I need to write an exponential growth model given the number n of incidents, okay, t years after 96. So not just for the 7th year, I want to model for any year. Okay, so now even though I just said it's y equals, for this problem, we're going to say, okay, the number of incidents that I'm solving for is now n. So for my first, I'm going to say n equals the initial, 2,573, 1 plus the rate, 0.92, and for any number of years, so I'm just going to leave this as a t. Now I can clean that up a little bit just by adding the 1 and the 0.92. All right, so this problem has a percentage increase of 92%, but what's the growth factor? 1.92. Okay, the problem also tells me that t is the number of years after 1996. So about how many incidents were there in 2003? Well, how many years since 1996 is 2003? 7 years. All right. So to solve for 2003, n would equal my initial 2,573 times 1.92 to the 7th power. So after 7 years in 2003, we can say that there were about 247,785. We'll just round. Incidents.
What?
All right, so now let's graph what we just saw. So we had the equation n equals 2,573 times 1.92 to the t. Okay? Now, with any kind of growth, we always plot what 2 points first?
0, 1, 1B.
0, 1, 1b.
Oh, you full grown. I want to watch that video now.
Okay, now what's the base? What's b?
2,573.
No. What's being raised to the exponent? 1.92. So 0, 1, 1, 1.92. Okay, so now I have to think, okay, is there an a that is multiplying the y values?
2,573.
Right, so every y value needs to be multiplied by 2,573. So just like graphing any normal exponential, you would do 0, 1, 1b, and then take the y values and multiply them by a. So that gives us these 2 points. I'm not going to have enough room. 0, 1 times 2,573 is 2,573. Okay? And the point 1, 1.92 times 2,573 is 4,940. Okay, now look, these points should make sense. 0 is the time since 1996. So if it's been 0 years, shouldn't I have just the amount that I started with? And look, 0, here's the amount that I started with. In 1 year, I should gain 92% more, right? Well, this is just the original times 1.92 to the first power. Now, another point that's going to help us plot all this is the point that we found a moment ago. After 7 years, there were 247,785 incidents. Okay? So let's plot these 3 points. To do this, I need to figure out what scale I'm going to use. So the years since 1996, here I have 0 years. 1, 2, 3, 4, 5, 6, 7. Okay? Now, I'm going to count by about 25,000 because I need up here to be around 250,000 because this is 250. So I'll label every other one by 50,000s. So 50,000, 100,000, 150,000, 200,000, 250,000. It was important to have this third point, this 7, and about 250,000, because our first 2 points are here hit like 0, 2,000, and 1, almost 5,000, which are both very small in respect to the 50,000 that we see. So we have like this point and this point. Yet by 7 years, we're almost to 250, to 250,000. Okay, so now we have a good 3 points. And again, to find these 2 points, another way you can think about it is at 0 years or at 0 time, you're always going to have your initial. And after 1, it'll always be the initial times the growth factor, because that's just the growth factor raised to the first power. So now that I have 3 points, I'm going to draw a curve through them. Remember that it's exponential growth, so it kind of rises up through. And our curves might look a little bit different from each other's. These are estimations. Right. Okay. So now the last question was to estimate the year when there were about 125,000 computer security incidents. So how am I going to do that? How am I going to estimate for 125,000? Well, I could go to 125,000 here on my graph. Okay, that meets right here, which is about how many years?
About 5 years, 6 years.
A little bit more than 5 years, right? Between 5 and 6 years. So real quickly, to go through all this again, I want to identify the initial amount. What's the initial amount?
A, no, A.
In this example right here, that'd be 527. Okay, what's the growth factor?
The growth factor is the
1.39 is the growth factor. And the percent increase is
is
what was added to 1?
39.
Yeah, we added 0.39, so that's 39%.
Wait, can you wait till we write that?
Okay, now exponential growth functions are used in real life situations involving compound interest. Okay, and this is the formula for compound interest. Compound interest is interest paid on initial investment called the principal and on previously earned interest. So you're getting interest on your interest. All right, it's a nice thing. If you're only earning interest based on the initial amount, the principal, that's called simple interest. Okay, so compound means, yeah, we're just going to keep, like, here's some interest. Now we're going to compound the next set of interest based on how much money you now have. All right, so let's define these things. P is the principal. That's just the amount that you invest. Okay, R is the interest rate. T is the years. And N is the number of times compounded per year. So if I say it's compounded weekly, that would be 52 times per year. Monthly, that'd be 12 times per year, and so on. So let's see that in action. You deposit $4,000 into an account that pays 2.92% interest, annual interest. Find the balance after 1 year if the interest is compounded with the given frequency. Okay, so what's the principal? What's P? P equals 4,000. That's the amount that we invested. All right, what's the rate?
The rate is 2.9.
2.92%. So what's that as a decimal?
0.299.
0.0292. Okay, remember that we have to move the decimal twice. The time that we're looking at is a year. And the N is going to change between part A and part B. Okay, so part A, if it's compounded quarterly, what does N equal? How many times per year is quarterly? 4. So, to figure out how much money I have in my account, I take the 4,000, 1 plus my interest rate, 0.0292, over 4, to the 4 times 1. Now, what the formula doesn't show you that I think you should include is like an extra set of parentheses here and a set of parentheses there. All right, even though 4 times 1 in this case is just 4. That way you know to do this first, 0.0292 divided by 4, then add 1, and then before you multiply it by 4,000, remember that you have to do exponents first. So whatever this all is, raised to the 4th power, times 4,000 will give me the amount after 1 year. All right, so if we compound quarterly at 2.92%, after 1 year, we should have $4,118.09. Okay? Now, what would you expect for compounded daily? Should you have a little bit more or a little bit less?
A little bit
Less.
Let's see what happens. Okay? Because I mean, what's happening here is that your rate is getting divided by the number of times a year, right? So we can't give you 2.92% every single time. I have to split that up 4 times. But since I'm not just doing it 1 time a year, right, I have to take my number of years and multiply it by how many times I'm going to do it per year. So in my second example, for daily, I have 4,000, 1 plus 0.0292 over, if it's daily, how many times is that a year? 365. So I'm going to put an extra set of parentheses on that. Oh, not 4 times 1. It's to the 365 times 1, which is just 365. Okay, so we put that in our calculators and figure out how much that would be. All right, so after a year compounded daily, I have almost the same thing, $4,118 and about 52 cents. So the more times compounded per year, the slightly more that you should have in your account. Okay, and so that's compound interest. Goodbye.